Welcome. In this video I'm going to show you how you can perform a Welch One-way ANOVA using Python. Specifically I'm using Jupyter Lab and I'm using Python version 3.8. Now this video will focus on how you can calculate a Welch One-way ANOVA, not so much on if you should. There are quite some articles about which test you should actually use if you want to compare different categories and their means. So I will simply focus on how to actually perform this test. To do that, I'll first need some example data. So I'll load pandas in and then load my data using the head function to show the first 5 rows. So I actually don't need all of this information. I only need one field or one column that can actually determine the categories and one that is a scale variable for the averages. So I'm going to be using location and overall grade. That was the grade the students actually gave the course, and just select those and remove any missing values then, so rows that have one of the two missing, and that's the data I'm going to be using. Now, one of the easiest ways of performing a one-way ANOVA is perhaps using the Pingonian package. If you've never used it before, you can use a pip install. That goes for any of the packages, and then simply import Pingonian as PG. Then after it's loaded, I can use the ANOVA function that requires the scale variable, the grade, and the between is for the categories and which data I'm using. In this case I named it selected data, and then I can just show the result. It will show me the degrees of freedom for both the first and the second one, the F statistics that's being used, and the uncorrected p-value. And this one we can actually ignore for now. The p-value is probably the most important. It's the significance sometimes reported in SPSS. And if it's below 0.05, we would usually then say that we reject the null hypothesis, which is that all of the means are equal in the population. So at least two of them should be different, or we can say that location has an influence on the average that the students gave the course. There's also Stats Models API that can do the same thing. So we load the Stats Models API, and then we can actually use the stats one-way and then one-way ANOVA. And now we can simply use that function to get our results. And as you can see, it has the same values, the 10.195, that's over here as well, and also the 0.0005, so far below the usual threshold of 0.05. I also made my own function for various of these tests, so if you want you can actually import it using HTTP import. That's not my library, but then you can actually use to load a library from GitHub. It's actually only a function, not an entire library. It uses some other libraries, for example from statistics, which comes with Python, the normal, dist, and variance, from SciPy, the F and the chi-square distributions, and the log from NumPy. And then you can just load the function using the HTTP import and then type in this address. That's my GitHub account. And then I only need that means test function. And after that, I can simply say, well, I'm going to using that means test function, my selected data, the groups, the scores, and which test to use, in this case Welch, and that should give us the same results again. If you don't want to use any libraries besides pandas, it is possible. Then you have to follow the formula, and one of the things is that the Welch test actually uses the Cochrane test statistic. I have a separate video on how to calculate that, so I'm not going to repeat all of that here. Here's just the code for that. It's the sample sizes we need, the averages and the variances. That all gets then combined into one result. We determine weight, which is the sample size divided by the variance of each category. We sum all of those, we adjust the weights by that sum, calculate a weighted mean, and then can calculate the Cochrane statistic. So after that we actually now need for Welch to apply a correction, which is done by first calculating, let's call it lambda, which is 1 minus those adjusted weights squared divided by the number in each category minus 1. So I can simply I have all those results. I already have those adjusted weights. So I square those and then divide by the number in sample size in that category. The adjustment itself is then calculated by taking the number of categories, that's k minus 1, and then 2 times k minus 2 over k plus 1 multiplied by that lambda. So to get the number of categories, I can simply use len of my results table, because that should give me those 3. And then the adjustment is simply exactly that formula. Finally, the Welch statistic is then the Cochrane statistic divided by that adjustment. And in this case, that gives us finally that 10.195 that we saw earlier as well. The first degrees of freedom is k minus 1. So that's going to be 3 minus 1 equals 2. And then the second is the k squared, the number of categories squared minus 1 divided over 3 times that lambda. And that gives us the 26.07. This follows an F distribution, so we can load that using SciPy. So we import the F for the F distribution, and then we can use the so-called survival function to find the p-value that goes with it. So that will show us the probability of having an F statistic of, what was it? We had an F of 10.195 with these degrees of freedom or more, if the assumption about the population would be true, which is that all means are equal. And here we get, again, the same p-value. If you really want, you can avoid pandas as well. I'm doing that in an appendix. I won't go over all the steps. I actually first then create the data without using pandas. So I convert the pandas data frame to simply lists, which is from Python. The length can then be used from Python's own function for k, and then you can simply follow the exact same steps as we did with pandas, but we then actually have to loop over all the categories each time to calculate everything. So for example, for the sample sizes, I need to loop over all the samples, all the categories, in order to actually count those. So that's being done all in here. So it's the exact same steps. It's just doing it with loops, and it should in the end give the same results. If you want, there's one function for it that I made for the Welch ANOVA, and that should in the end, it's actually just simply the same as those steps earlier, and that should give me the same result as well. Alright, I hope this was helpful. Thank you for watching, and see you in the next video.